Good morning everyone. So welcome to my YouTube channel Math Support. So today we are going to see 8 lectures on group automorphism. So let us start today's session now. Okay. So today we will make some basic things clear. Okay. So I am doing this question, or you can say it is theorem. Okay. Theorem. You can say theorem 1. Okay. No problem. So let G be a cyclic group, okay, and F belongs and cyclic group generated by element A. It means, what does it mean? It means A is generator of G. Okay. And F1, F2 are, and F1, F2 be automorphisms of G such that F1A is equal to F2A, then F1 is equal to F2 on G. Okay. So proof. So it is saying that if you have a cyclic group and you have two automorphism F1, F2, they have the same image at the generator of the group, then they will be equal on the group. Means both the automorphism will be same. Okay. Given that F1 A is equal to F2 A, let X belongs to G. Since G is cyclic and A is generator of G, there exists K integer such that, because every element of a cyclic group is some power of generator. Every element of a cyclic group, some power of a generator. So there will be some integer such that this will happen. Now, what is F1X? F1X is F1 A to the power K. Okay. But this is equal to, but F1 is a homomorphism. If F1 is a homomorphism, because automorphism is always a homomorphism, so I can write it F1 A to the power K, but F1 is equal to F2. F1 is equal to F2. So I can put in place of F1A, F2A. Again, by property of homomorphism, because F2 is a homomorphism. I can write like this. Okay. So this is implies, what is this? A to the power k is x. So this implies F1x is equal to F2x for all x belongs to G. So this implies F1 is equal to F1 on G. So this implies F1 is equal to F2 on G. Okay. So this is done. Okay. So this is done. Okay. So theorem 2. Let G be a finite cyclic group of order n. Okay. Order n. Then G is equal to then G is equal to automorphism group of G. Then automorphism group of G is equal to Fm such that Fm x is equal to x to the power m for all x belongs to G. Okay. Okay. Comma. So you write symbolically. It will be better. Okay. For all, write symbolically. It will be better. For all x belongs to G, comma, m is less than equal to, m is greater than equal to 1 and is still less than n, and okay, m, this is 1. What is the meaning of this bracket m comma n? The meaning of this bracket is GCD. We are taking greatest common divisor. So this is meaning of GCD. Okay. So I will write, this is the meaning of GCD. We are taking GCD of m and n. Okay. This is the meaning. So I am writing in comment in the proof. Let A be generator of G. Okay. Now take let F belongs to automorphism of G by previous lecture, group automorphisms by previous lecture, group automorphism. Lecture 7. We have that f a will be some a to the power m. It will be mapped. Generator will be mapped to this element. Here m is less than equal to n, and this mn is equal to GCD of m and n is equal to. It means GCD is 1. It means relatively prime. M will be less than, is to be less than n, and greater than equal to 1. It means m is relatively prime. The GCD is 1 means m is relatively prime to n. The meaning is same. Okay. When you have two numbers, their GCD is 1, it means they are relatively prime. Okay. So now, take so let x belongs to G. Let x belong to G. Then here exists K belongs to I such that x is equal to a to the power k, because G is cyclic. Every element of a cyclic group is some power of a generator. That is why you take any element from G, it will be some power of A. Okay. So this is cyclic. Now f x is equal to f a to the power k. This is nothing but f a to the power k. So what is f? This is a m to the power k. So I can write it a m k. But this is nothing but a to the power k to the power m. So this is x to the power m. F x is equal to x to the power m for x belongs to G. Okay. So we write. So this implies we write f x is equal to fmx. We write fmx is equal to fmx is equal to fx for all x belongs to G. Since f is identified by m. Okay. Then fm is equal to f on G. Okay. So every f belongs to automorphism group G. This implies f is fm. Here this is less than equal to n, and GCD of mn is equal to 1. And what is the order of this group? Order of this group is nothing but phi n. Euler phi function. What is the order of this group? Phi n. It means all cardinality. So I can, how to write the order of set? The number of elements. What is the meaning of phi n set? Number of elements m such that m is in this range and relatively prime to n. It means number of elements in the set GCD is 1. GCD of m and n 1. Okay. So we have whatever element you take in automorphism group, it is of the form Fm, where m is relatively prime to m and greater than equal to m and less than n. And order of that group is also of number of elements of such type of m's. So what does it mean? It means that this implies that automorphism group is nothing but Fm. Okay. Okay. So automorphism group is nothing but Fm such that Fm x is equal to x to the power m. Okay. For all x belongs to G, m is this range and GCD of m and n is equal to 1. So we have proved it. So this is proved. Okay. So this is proved. Okay. Now we are going to do one example. Okay. So before doing that example, okay, let's do that example. So that the group of automorphism of a cyclic group is abelian. Okay. So group, you take any cyclic group, the corresponding automorphism group AUTG is abelian group. Okay. Let G is equal to is a cyclic group, be a cyclic group generated by A. So, okay. Then the two cases are, then there are two cases. Case one, G is infinite cyclic group. If two cases arises, first is first case is G is infinite cyclic group. G is infinite cyclic group. Okay. If G is infinite cyclic group, then there will be two generators. If G is infinite cyclic group, okay. If G is infinite cyclic group, then there are two automorphisms. One is identity map, and another is F. Okay. So identity map will map A to A. Okay. And F will map to A inverse. Because a infinite cyclic group has two generators. A infinite cyclic group will have always two generators. Okay. From here, what we have? We have this map will be identity map. And what will be this map? This map will imply goes to X inverse. Okay. You take any element, so it will be A to the power K, and then you will put A to the power will come out A inverse A to the power K. So it will show like this. Okay. So this is happening. So I am writing in bracket every infinite cyclic group has two generators, A and minus A. Once you know generator A and minus A will be also generator. So how A automorphism come? A goes to A and A goes to another generator. That is why. So this will imply for all X belongs to G, and this will imply X belongs to X is equal to X inverse for all X belongs to G. So in a automorphism of G, how many elements are there? This is identity map, identity automorphism, okay, and F such that fx is equal to x inverse for all x belongs to G. Okay. So what is the order of 2? What is the order of this group? Order of automorphism G. How many elements are there in this group? 2. We noted every group of prime order is cyclic. Every group of prime order is cyclic. Okay. Every cyclic group is abelian. Okay. Every cyclic group is abelian. So this is prime number, and we know that prime numbers are a group of prime number order is cyclic. So this implies automorphism of G is cyclic, and cyclic group is abelian. So this implies automorphism group G is abelian. Okay. So we are done. So in this case we are done. Now we are doing another. Now case second we are doing. What is case second? So case second we are doing. Case second. Okay. So I'm writing if G is infinite cyclic group, then AUTG is abelian. Okay. Now case second. G is finite cyclic group. G is finite cyclic group. It will have order n, some n. Okay. Second case is G is finite cyclic group. Let's say order of G is n. Then by theorem 2, we have what is automorphism group of G? Automorphism group of G is nothing but, what is this? Fm such that Fmx is equal to x to the power m for all x belongs to G. Okay, m is in this range and GCD of m and n is equal to 1. It means m is relatively prime to n. Okay. Now you take any two elements. So now let F Fr Fs belongs to automorphism of G. Okay. Then Fr A means what? A to the power R, and Fs A means what? A to the power S. Okay. Now Fr Fs, what is this? This is equal to Fr Fs A. What is this? Fr A to the power S. And what is meaning of this? As R. Okay. Now I can write this A to the power SR. Now I can write it A to the power F. What is this? This is FR A to the power S. Now what is this? FS FRA. So what is this now? This is implies FS come FS and FRA. This implies FS A is equal to FS FR. Okay. By theorem 1, we have, because this map FR compose FS, the product, this map is a automorphism and they are equal on generator, so they will be equal. Okay. So this implies FR FS FS FR. So this implies automorphism of G is abelian. Okay. If G is finite group, finite cyclic group, then automorphism of G is abelian. Okay. Hence, if G is cyclic group, then group of automorphism of automorphism of G is abelian. Okay. So this is done. Okay. So you take any cyclic group, the corresponding automorphism group will be cyclic. Okay, abelian. So it will be abelian, sorry. It will be abelian. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.